So we did this right with the help of the table, right? Which of them will form a precipitate and which of them will not. So another question is this, that we are mixing these two. The blue ones are anions, red ones are cations. And after mixing, you can see that, right? On the right hand side, it is a solid formation, right? A solid. So that is to say, a precipitate has formed. So they are asking that which cation and anion combinations are compatible with the observed results. That is to say, which combination of cations and anions are going to form uh, a precipitate, right? That is the question. And these are the combinations. So let's see how do we proceed about this. So whatever combinations we have available for the singly charged, we'll pair up the things. Okay, we'll pair up them like this. So Ag plus NO3 minus K plus NO3 minus, and then Cl minus was there. So Ag plus Cl minus K plus Cl minus. And for doubly charged, possible combination for doubly charged are again CaCO3, okay, and CdCO3, okay. Now we have to only consider 1:1, right? Because only 1:1 have been formed. See, oh, we can also say that CaCl2 will be formed, right? But as we can see that the number of cations are same as number of anions. So red spheres are same in number as the blue spheres. So we are only considering 1:1. Okay. So that is why we are not considering CaCl2, CaNO3 whole twice, CdCl2, CdNO3 whole twice, because we are considering 1:1, right? So among these possible pairs, we know that KCl, AgNO3, KNO3, right? They are all going to be soluble. So what we are left with is precipitate will come only in the case of AgCl here. Okay. And then if we'll check, it will come in the case of calcium carbonate and it will come in the CdCO3 case, right? So this is how it will be formed. So this was the problem. Now, next question is an aqueous solution containing an anion represented by blue spheres is added to another solution and the following result is obtained, right? So which cation and anion combinations are compatible with the observed results, right? So here again we can see that 2, 4, 6, 8. 8 is to 12, right? This is the ratio, right? Blue spheres are anions, right? Cations are how many? Cations are 12 and anions are 8. So simplest ratio is C3A2. So 3 cations and 2 anions, right? This is this is what we have to search in the diagram, right? So go ahead and tell me which of these will be possible, right? And then we'll see. Sanjita, you are at home or outside?
Sir, I'm outside, but I'll reach home in another 10 minutes or so.
Okay, okay. You're coming back from swimming?
Yeah.
Okay.
So can it be Mg and PO4 because
Yes, 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 yes. It can be. Yes. Very nice.
and Zn and PO4?
Yes. Also check. You have the table, right? We have a table also, right? Where it will show us the solubilities of the cations and anions, right?
Yes, sir.
Remember? So it is either magnesium or zinc phosphate, right?
Yes, sir.
Right. Sanjita, see, we need three cations and two anions. So the charges have to be balanced, right? So if we have magnesium phosphate, so it will be like Mg3PO4 whole twice, right? See how they are formed. Suppose Mg is 2 positive and PO4 is 3 minus. So how we will write the? We'll cross multiply this, right? That's what we do. It's charge here, it's charge here. Meaning thereby it will form Mg3 and PO4 2. Because only then the charge will balance, right? There are 3 Mg, so total charge is 3 Mg 2 plus will have total of 6 plus charge. And 2 PO4 3 minus will have 6 minus charge. So that is how they will become neutral, right? Got it? Okay. So this is how it is. Similarly in the zinc. Now we are going to consider this acids, bases, and neutralization reactions. Okay. So it was in 1777 that Antoine Lavoisier he proposed that all acids contain a common element, oxygen. In fact, the word oxygen is derived from Greek phase. Gen means to generate and oxy means acid former. Okay. But again, Lavoisier's idea has to be modified because when this British chemist Humphrey Davy he showed that hydrochloric acid, which at that time was muriatic acid, it's much better hydrochloric acid, contain only hydrogen and chlorine but no oxygen. So his studies suggested that the common elements in acid is hydrogen and not oxygen. So this is a little bit of history. Now, a relationship between acidic behavior and the presence of hydrogen ion in a compound was clarified in 1887. So nearly when 1900 was beginning, right? It was done by Swedish chemist Savante Arrhenius. Okay, we're going to read about him in much detail in higher classes. And Arrhenius, he proposed that an acid is a substance that dissociates in water to give hydrogen ions H plus, and a base is a substance that dissociates in water to give hydroxide ion OH minus. This is the this is the basic definition. An acid is HA, and you can see it is written aqueous, right? An acid is HA aqueous, H plus A minus aqueous. A base is MOH aqueous, M plus aqueous plus OH minus aqueous, right? So in these equations, HA is a general formula for an acid, for example, HCl or HNO3, and MOH is the general formula for a metal hydroxide like NaOH, KOH. So that is M is metal, okay, and A is some anion, okay, that is it. So H plus aqueous does not really represent the structure. Actually, what is happening is H plus is much too reactive to exist by itself. So H plus forms a bond with the oxygen atom of a water molecule and it forms a stable hydronium ion. So acid is actually in water it exists. It does not exist as H plus, but is exists as hydronium ion. So we will sometimes write H plus aqueous for convenience, okay, particularly when balancing equation, but we will more often write H3O plus aqueous to represent an aqueous acid solution, okay. So how do we write? We can also write it as HCl plus H2O gives H3O plus and Cl minus. It's the same thing. Or you can also write it as HCl aqueous and it gives us H plus aqueous plus Cl minus aqueous, right? HCl aqueous, H plus and Cl minus aqueous. Okay. So this is the thing. Okay. Now let us go to these acids. HCl, HClO4, HNO3, H2SO4, they are strong electrolytes and therefore strong acids. Okay. While CH3CO2H, this is the acetic acid. HF, they are weak electrolytes and therefore weak acids. Okay, we have studied about strong electrolytes and weak electrolytes. Strong electrolytes are those electrolytes which dissociate greater than 70%, right? So also you can see that acetic acid actually has four hydrogens, but only the one bonded to oxygen atom dissociates. Okay. So we'll study about it later also. So this is the structure, and the three hydrogens which are attached to carbon, they are non-acidic. Okay. Only the hydrogen which is attached to the oxygen is acidic. Right. So hydrochloric acid is said to be monoprotic acid because it can provide only one H plus ions. But sulfuric acid H2SO4 is called a diprotic acid because it can provide two H plus ions. Phosphoric acid H3PO4 is a triprotic acid and it can provide 3H plus ions. Okay. Now with sulfuric acid, the first ionization or the first dissociation of H plus is complete. That is to say, the first proton is dissociating fully. See, okay. It is shown by single arrow that the reaction is not coming backward. But the second proton, as you can see, it is shown by a backward arrow also, meaning thereby they can also combine and the reaction can also come back. Okay. So it means that the second dissociation is not complete. Okay. With phosphoric acid, none of the three dissociations are complete. Okay. So the first dissociation is also incomplete. Second is also incomplete. See, and third dissociation is also incomplete. So incomplete dissociation are shown by this back arrows also. Okay. Complete dissociation are shown by one full forward arrow, right? Completely dissociated. So in sulfuric acid, only the first one is dissociating in the in complete manner, right? So again, bases, they also like acids can also either be strong or weak depending on to the extent to which they produce OH minus ions in aqueous solutions. Okay. Now, most metal hydroxides such as NaOH, KOH, or barium hydroxides, they are strong electrolytes and strong bases, but ammonia is a weak electrolyte and a weak base. Okay. Ammonia is a weak base because it will react to a small extent with water to give NH4 plus and OH minus ions. In fact, aqueous solution of ammonia are often called ammonium hydroxide. Okay, right. Although this is a misnomer because the concentration of NH4 plus and OH minus ions are low. But see, this is how ammonia is a gas, water is a liquid, and after dissolving, we have to write NH4 plus aqueous and OH minus aqueous. Okay. So the reaction of ammonia with water takes only to a small extent, about 1%. Okay. Most of the ammonia remains unreacted, and therefore we write the reaction with double arrow to show that a dynamic equilibrium exists between the forward and reverse reactions. Meaning to say that the rate of the forward and reverse reactions are equal. That is what we mean by dynamic equilibrium. We'll come to more of this, but for the moment, we have to double arrow for us indicates that this dissociation is not one-sided and it is only partial. Okay. So see, this is aqueous ammonia. Okay. They have labeled it ammonium hydroxide, but anyways. Now again, naming acids. Most acids are oxo acids. Okay. That is, they contain oxygen in addition to hydrogen. Okay. So when dissolved, an oxo acid produce one or more H plus ion and an oxo anion. Okay. Like the one listed in this table. okay, in the forward table. First, we'll just consider this. These are the strong acids, these are the weak acids. Above this, we have strong acids, nitric acid, hydrochloric acid, hydrobromic acid, sulfuric acid, perchloric acid. Whereas H3PO4, HF, HNO2, and CH3CO2H, H3PO4 is phosphoric acid, HF is hydrofluoric acid, HNO2 is nitrous acid, CH3CO2H is acetic acid. Okay, they are weak acids. Similarly, for the bases, above this we have strong bases, KOH, potassium hydroxide, NaOH, sodium hydroxide, BaOH whole twice, barium hydroxide, CaOH whole twice, calcium hydroxide, and ammonia is a weak base. So this is the, so you need to keep this table in mind. Okay, important. This is important. Okay, and these are the, again, this table is important. You must be remembering this, and gradually you'll. So nitrous acid, and after taking H plus, we are left with NO2 minus ion, which we call nitrite ion. HNO3 is called nitric acid. After taking H plus, we are left with NO3 minus, which we call nitrate ion. H3PO4 is called phosphoric acid. After taking all the three H plus, we are left with PO4 3 minus, right? Because 3H plus have been taken out. This we call phosphate ion. H2SO3, this is called sulfurous acid. SO3 2 minus is called sulfite ion. Sulfuric, us is ite and ic is 8. Sulfuric acid, H2SO4. After taking 2H plus, I am left with SO4 2 minus, which we call sulfate ion, right? HClO, this we call hypochlorous acid. Hypo means less than one oxygen. I'll just explain more. Hypochlorous acid is HClO. So we again take out ClO minus. This we call hypochlorite ion. HClO2 is called, just like nitrous acid, HNO2, it is called chlorous acid. Okay. So even hypo means even one oxygen is less as compared to HClO2. That is the chlorous one. When we take H plus out, we get ClO2 minus. This we call chlorite ion. HClO3 is chloric acid, just like nitric acid, HNO3. So we'll call it chlorate, ic is 8, right? And after taking this, we are getting ClO3 minus. HClO4, this per means having one oxygen more. So this has one more oxygen as compared to chloric acid. So this is called perchloric acid. I take H plus out, I get ClO4 minus. This we are going to call perchlorate ion. So this table is again important. I have already said. Take it. So you need to remember this. Okay. Again, the names of oxo acids are related to the names of the corresponding oxo ions. Okay. This is we just discussed. Ite or 8 depending on whether OS acid or ic acid. Ic acid will 8 and OS acid is ite. Okay. Acid with fewer oxygen has an OUS ending, and the acid with more oxygen has IC ending. For example, HNO2 is called nitrous acid because it has fewer oxygen, and it will call nitrite ion, while HNO3 is called nitric acid because it has more oxygen, and it is going to give NO3 minus, which we call nitrate ion. Okay. So this is the equation. See. So when this I can write, or I can also write this as HNO2 aqueous, and it is dissolving H plus aqueous. I can also write this, or I can write this above equation, right? I can also write this. Similarly, for nitric acid, I can write HNO3 aqueous. Okay. And you can see that HNO3 nitric acid, only single arrow is there because it is a strong acid. HNO2 is a weak acid. So both forward and backward arrows are there, right? Hypochlorous acid gives hypochlorite ion, chlorous acid gives the chloride, chloric gives the chlorate, and perchloric acid gives the perchlorate ion, the same table which we discussed. There are small number of other common acids such as HCl, which do not contain oxygen. For this, we use the prefix hydro and the suffix ic. Acid are used for the aqueous solution. So hydro and chlorine is chloric acid. HCN is hydrocyanic acid, right? Okay. So this is the thing. So try this HBRO aqueous and H2S aqueous. We have to name, right? So HBRO is there and H2S is there. So this is hypobromite ion it has. Okay. So we are going to call it hypobromous acid. You can refer to the table anytime. You can open it in alternate window and open anytime, right? Next, H2S, it is not an oxo acid, but it will give sulfide ion, okay, when dissolved in water, right? As a pure gas, H2S is named as hydrogen sulfide. If it is pure gas, it is named as hydrogen sulfide. In water solution, we will call it hydrosulfuric acid. Okay, H2S is called hydrosulfuric acid. Now, do 4.16 and 4.17. Okay, let me know when you are done. Okay.
So is the first one hydroiodic acid?
Yes, write it and send it to me.
Okay.
Both 4.16, 4.17.
So BrO2 is a oxo anion, right?
You can open this and then you can refer to this, right? Got it?
So it's not there.
What is not there?
So, oh, never mind, I got it.
Chlorine is there, so you have to tell for the bromine, huh?
Yes, sir.
Got it?
Yes, sir.
Sir, can I leave and rejoin? I've just reached home.
Yes, please.
So can you show where the table is?
Yeah.
Chapter 4.
So you can also open it from now. Okay.
So I sent the answers.
Okay. hydroiodic acid, okay, and bromous acid, okay, bromic acid, okay, CPO3, H2. Yeah, it's correct. Okay, Sanchita is back. Now, neutralization reactions, these are, you must have heard about them. Not, then what happens? We mix acid and base and we get water and salt, right? This is a neutralization reaction, acid, base, you're going to get water and a salt, Na, right? So salts are strong electrolytes. We can also write the neutralization reaction provided we have a strong acid and strong base. If we have a strong acid, then I can write Ha as H plus aqueous, A minus aqueous. If I have a strong base, I can write M plus aqueous, OH minus aqueous. And the products are this H2O liquid. This I cannot write any other way because it is a molecule. And salt I can again write as M plus A aqueous and A minus aqueous. So M plus and A minus will cancel out and we will have net ionic equation as H plus aqueous plus OH minus aqueous giving H2O liquid. Or we can write the same thing as H3O plus aqueous. Instead of H plus aqueous, you can write H3O plus aqueous, right? So in this case, it will become 2H2O liquid. Okay. Now, if the acid is weak, then I cannot write HF aqueous as H plus and F minus aqueous. Okay. In this case, I cannot write HF aqueous as H plus aqueous and F minus aqueous. Plus the base I can write whatever it is, M plus aqueous and OH minus aqueous, H2O liquid. And again, the salt will be M plus aqueous and F minus aqueous. M plus will cancel out, but F minus aqueous will remain, right? So here we have written this as for this KOH and HF, right? So I'll just write it. KOH aqueous plus HF aqueous gives H2O liquid plus KF aqueous. So KH aqueous I can write K plus aqueous. OH minus I write usually HO minus because negative is on the oxygen, not on the hydrogen. But you can write for the meantime OH minus aqueous. But remember the negative is on the oxygen, right? Plus here I cannot break it because it's a weak acid. I have to keep this as H2 liquid and the salt again, potassium salt will dissociate K plus aqueous, F minus aqueous. And then I can cancel out the common ions, right? K plus only will cancel out. And finally, I'm going to get HF aqueous. I'm rearranging this plus OH minus aqueous is going to give me H2O liquid plus F minus aqueous, right? So this is how we are going to do. See. So this is what they have written, right? HF aqueous plus OH minus aqueous, H2O liquid plus F minus. So now we have to write both an ionic equation and a net ionic equation for the neutralization reaction of aqueous HBr and aqueous barium hydroxide. Okay. So first we will write the common equation. See, We are writing like this: 2H plus aqueous plus 2Br minus aqueous plus barium 2 plus aqueous plus 2OH minus aqueous. And it goes to 2H2O liquid plus 2Br minus aqueous plus Ba2 plus aqueous. Same thing. First, you have to write a normal equation, okay? A normal equation you will write like this. Okay, let us. This is the acid, which we are because we have to balance it. Barium hydroxide, aqueous, and this is going to give me salt and water. So, water, and I'm going to get this salt, barium from my aqueous. And then I start breaking them. See. So first we write the balanced equation. After that, we are going to write the normal equation, right? Okay. So that is the thing. That is the main thing. Okay. Now 4.18. Excuse me. 4.18 4.19 करके भेजे, शाबाश। Take your time but send it. बैलेंस्ड आयनिक इक्वेशन मतलब आयंस में ब्रेक करके लिख देना सब कुछ। पहले तो नॉर्मल लिख लिया करो, उसके बाद आयंस में ब्रेक करके लिखो। ओके, received from Sanchita. Aqueous. Whenever we write ions, we must put aqueous. Okay, Sanchita.
Okay.
Hello, you can hear me, Sanchita, right?
Yes, sir.
Okay. And also in the final equation for the B part, 4.18, you have forgotten to write negative on CH3CO2 minus, huh? Okay.
Yeah.
So write aqueous everywhere because else people will not give you marks. Very good. Same, everything is correct except that aqueous thing. Okay. Yes. Good. Same thing is for Ananya. Okay. See,
Yes.
aqueous is very important for part. Okay. Because that is where the ions are residing. Okay. So we must write that thing. Okay. Now solution stoichiometry. Okay. So we know how to calculate, right? We know that if we know the balanced equation and the moles of one substance, then we can calculate the moles of all the species, and then we can calculate the mass of the species also, right? Now let us consider this particular equation. Now they have asked that stomach acid, which is a dilute solution of hydrochloric in water, can be neutralized by reaction with sodium hydrogen carbonate according to this particular reaction. Now, they have asked how many milliliters of 0.125 molar NaHCO3 solution are needed to neutralize 18 ml of 0.1 molar HCl. See, same thing, nothing. First, we'll write, we have to relate HCl and NaHCO3. So I will write like this: mole HCl divided by 1 is equal to mole NaHCO3 divided by 1. And moles I can write as molarity into volume in liters. So molarity, or right, so molarity of HCl is 0.100. Volume in liters, 18 milliliters mean into 10 to power minus 3 liters. Mole of NaHCO3 will be 0.125. This is the molarity, and into volume in, here it will be in liters, right? Because we are equating the mole. So we can solve this and calculate the volume in liters. Okay. And after calculating whatever the volume is in liters, to convert it into milliliters, we multiply by 1000, right? Because in 1 liter there are 1000 milliliters. So this is a simple method. You don't have to follow what they are doing or whatever, right? You got what I said, right? Clear, right? Ananya, Sanchita?
Yes, sir.
Yes, sir.
Okay. So that is what they have also done. See the same thing they have done. And also I told you that, yeah, we'll just keep on liters and we'll convert into milliliters. So we will get 14.4 into 10 to power minus 3 liters, which is equal to 14.4 ml, right? So this is how we have to do. Now you have to do 4.20 and 4.21 and send it to, okay, that is. Same concept.
Sir, I sent the answers.
Okay. Four point two zero you sent. How much you got?
10 ml. Four point two one. Also, you're getting 0.0547 molar. Yes. Sanchita has also sent 10 ml and 0.055. Okay, 0.547 you should write, but it's okay. Very nice, very nice, very nice. So we'll just come to titrations in a while. Okay. So
See, now we are going to study about how to measure the concentration. Okay. Measuring the concentration of a solution, right? This is what we are trying to do. Okay. How to measure the concentration of a solution. So, for example, the concentrations of ions such as H plus, OH minus, Fe3 plus, magnesium 2 plus, calcium 2 plus, and Cl minus, they are important in the quality of water used for drinking, irrigation, and industrial processes. So we have to measure the concentration of the solution and check if these ions are present. Okay. So also solutions prepared by the methods described in section 4.1 may not result in the exact molarity. Okay, calculated by dividing moles of solute by volume of solution, right? This error or discrepancy arises because chemicals often cannot be purchased in their pure form, or they react with other chemicals in the solvent or in the air. Okay. So what we do is a technique frequently used for determining a solution's exact molarity is called a titration. Okay. This is what is meant by titration. So titration is a procedure for determining the concentration of a solution by allowing a measured volume of that solution to react with the second solution of another substance, which is called the standard solution, whose molarity or concentration we know. Okay. And by finding the volume of the standard solution that reacts with the measured volume of the first solution, the concentration of the first solution can be calculated. Okay. And it is necessary condition that the reaction must go to completion. Okay. And have a yield of 100%. We'll come to this, but anyways. So all this is good, but whatever we have to do the same thing. Mole NaOH by 1, mole HCl by 1. Okay, there is no change there. This is only a new thing which we have learned, that during the titration, what we do is we have a standard solution whose molarity we know, right? And we titrate the process is called titration. Okay, this is for determining a solution's exact molarity. This is we call titration. So it's the same thing. We don't need to look at this. So this is how titration is done. And how do we know that the neutralization has taken place? Okay, we add a small amount of indicator. Okay, and what happens is that as soon as the reaction is complete, okay, that the equivalents or moles, whatever the ratio is there given by stoichiometric equation, that is equal, then immediately it changes the color. Okay, that is how it is happen. So how do our titration is performed? First, a measured volume of acid solution is placed in flask. Okay, and phenolphthalein indicator is added. Now base solution of non-concentration is added. So whatever we are adding here, this molarity is known. This concentration is known. So we'll keep on adding. So we can also keep a track of the volume which we are adding, right? So what is happening is until the indicator changes color. Okay, we keep on adding drop by drop by drop by drop until the color changes. And the reading the volume of the base from the burette allows calculation of the acid conversion concentration. So basically we know the volume, right? Whatever of this we have added, this is already known. The volume is already known. This volume is already known. And its molarity is something to be calculated. So you can see that it is the same thing, right? The same concept which we have to apply, right? Okay. So phenolphthalein is colorless in acid solution, okay, but turns red in basic solution. Okay. Next, we fill a calibrated glass tube called a burette with an NaOH standard solution of non-concentration and slowly add the NaOH to the HCl. Okay, we're adding NaOH to the HCl. So when the phenolphthalein just begins to turn pink, it means all the HCl has completely reacted and the solution now has a tiny amount of excess NaOH. So that is why we have to add drop by drop by drop. When just adding after one drop, it changes the color, we stop. Because now it just has one drop of excess of base in the solution. So when the solution is slightly basic, it starts changing the color. Okay. And that is how it is. Okay. Now we have to do the same thing. Determine the concentration of a solution using a titration process. So a 20 ml sample of HCl is titrated. So only the new word is titrated and found to react with 42.6 ml of 0.100 molar NaOH. What is the molarity of the hydrochloric acid solution, right? That is what we have to, that is what we have to see, right? So yeah, let's see that. Okay. Okay. Let's see. Let's see if we can do that. Let me know the answer.
So is the answer 0.213?
0.213 what?
Molarity.
Capital M, molar, you have to say. Okay?
Yes. Yes, sir.
Yes, this is the answer. Huh? Right?
Yes, sir.
See. So we don't need to do anything. We just simply need to apply our. Okay. So next you have to do this. Okay, waiting.
Sir, I've sent it.
Okay.
So even I just sent it.
Okay. Nice. So we are done till here. We have few more minutes, so let's do. Few more questions relating to this. So this is the homework which we I am expecting, but this I am expecting as homework. This is a homework, and the section before that is also a homework. 4.6. So 4.6 and 4.7 as homework. Now we come here. You can do 4.92. Seven five seven six 100. Okay. No, no. Both of you are getting 100 ml. Huh? Okay. Interesting. Check this. One sec. This is a titration, right? Let's call it titration. And this was the question, right? Burette contains H plus ions, flask contain HO minus, and each has a volume 100 ml. Okay. How many milliliters would you need to add from the burette to flask to nitri in the titration process? Okay. Anyways, I think you got it wrong. I don't think any one of you counted these molecules, or did you? Nobody did, right? Okay, no problem. We'll get back to this. We can come here. These are the titration problems. I'll just name it one sec. Titration problems. Okay. Yeah, we can do this. Open ठीक है, send me this. Okay. चलो ठीक है, मिलते हैं tomorrow. Okay. Do this and send it to me. चलो, bye. Lunch time.
Bye. Bye, sir. Thank you so much.
Okay, bye.
Bye, sir.
Bye.